SwayamPrabha. Digital India. Educated India.
Welcome to the class. Last time we have seen that the isentropic relations exist for the flows with inviscid and steady case, and then those isentropic relations for mass, momentum and energy equations we had seen. Using those relations we had proved the speed of sound is equal to under root gamma RT for the gases, and then we had also seen it for the other cases. Now in today's class we are going to study about the nozzle flows. These studies, whatever we have underwent in the last class and today's class, will be helpful for the studies or for the analysis of the turbine. So nozzle flow, we know that, let us consider that there is the nozzle which is of convergent divergent section, where as per the last class our information, if velocity is 0, then such conditions are called as total conditions. So let the nozzle inlet has total conditions. This is the nozzle inlet, this is the nozzle outlet, and this is our nozzle. Okay. So having known this as nozzle and this is inlet and this is outlet condition, we are saying that now, to start with, if inlet and outlet pressure is same, then there will not be any flow taking place through the nozzle. But this nozzle exit pressure, denoted by PE, is suppose decreased, then flow will start taking place in the nozzle. In our last class we had seen that if the duct is convergent and flow is subsonic, then it will act as nozzle. If duct is divergent and flow is supersonic, then it will act as nozzle. So initially there will be subsonic flow and convergent section acts as a nozzle, but it will not reach a critical condition to the minimum dimension, which we call it as throat. So it will still remain subsonic over here, and then that's why pressure will initially decrease, and then this divergent portion will act as a diffuser. So pressure will start to increase and it will try to reach to the exit pressure. Further, in the next experiment, if we decrease this PE to some value which is corresponding to G, then we will have further deceleration of the flow and we will still follow the subsonic curve path in both the nozzles. So this thing will continue till we will have a critical pressure in the exit, where we will have the convergent portion acting as a nozzle such that the Mach number at this minimum cross section will become 1, and then if we decrease the pressure below slightly to that critical pressure, then we will have this convergent portion acting still as nozzle and no property will change in this portion, and then we will have certain part of the divergent section will continue to act as nozzle. But if it continues to act as nozzle, then we will reach a state which will be B, but the exit pressure for us is corresponding to F. So it is not advisable for the flow that it should continue to get expanded in the nozzle. That's why intermediate shock will appear, and then that shock will give rise to the pressure of the flow and it will make the flow to be in subsonic range. And since the flow is subsonic and the section is divergent, it acts as diffuser such that pressure will rise and reach the state F. if we still decrease the exit pressure to E, then the shock will appear little late, but till that portion the convergent and divergent part of divergent nozzle would continue to act as nozzle, then there will be shock and then flow will be subsonic and then it will try continuing as diffuser. This process continues till a point where we will have exit pressure matching with the isentropic expansion case, and then in that case flow will be continuously expanded in the nozzle and we will have a nice expansion of the flow in the nozzle, and then we will have flow expanding or decreasing its pressure from state A, which is a stagnation condition, to state B. So, this is how flow would take place in a nozzle, and in this state, as we were doing the experiment where nozzle exit pressure was decreased. So, in this direction we are decreasing the nozzle exit pressure. So, as in initial case we had nozzle exit pressure and the stagnation pressure at the inlet are same. So, this state is 1. So, at the state 1 there is 0 mass flow rate going through the nozzle, but if we decrease the exit pressure slightly, then that means we have increased the mass flow rate of the nozzle, and then as we continuously decreasing the exit pressure, then we will continuously increasing the mass flow rate, but this increment will take place till only a critical value when we have minimum cross section reaching Mach 1, and then once minimum cross section is reached with Mach 1 and we have the nozzle subsonic part acting as nozzle, then in that case there onwards further any decrement in exit pressure will not change the pressure in the mass flow rate through the nozzle. In that case we are having in some of these cases we have the shock in the divergent portion, but this is not going to alter the mass flow rate. So, mass flow rate is frozen for the flow. So, this mass flow rate which is fixed at a state where Mach 1 is reached into this minimum cross section is called as choked mass flow rate for the nozzle. So, if we have choked mass flow rate, then there are two types of conditions which are possible, and one condition is called as over expanded flow, another condition is called as under expanded flow. These conditions correspond to the fact that in case of over expanded flow we are seeing over here where we are having shock in the nozzle. If there is shock in the nozzle means flow is expanded, but if flow would continuously expand till the exit, it will go to a pressure very lower than the exit pressure, which is not expected. So, this is called as over expanded condition. So, for that nature will provide a shock in the nozzle or maybe outside the nozzle such that this shock would give rise to the pressure, and such rise in pressure would match with the exit pressure. Such condition is called as over expanded, where we can see that there is a shock in the exit of the nozzle or there is shock in the inside the nozzle. Further, if we have pressure in the exit of the nozzle which is below the expected exit pressure for the isentropic expansion, then flow will continuously expand in the nozzle and will reach a pressure which is PB, but exit pressure is lower than PB. Such case is called as under expanded case, which are the pressures lower than this, and in this case we will have an expansion fan appearing in the nozzle exit, and then it would lead to expansion, continuous expansion outside the nozzle as well till the flow matches its pressure with the ambient pressure. So, these are the some details of flow through the nozzle. Now, we have seen that there is a choking condition, and for that we have to use this understanding of choking condition to find out mass flow rate, but before that we will try to find out what is the area Mach number relation. We know that rho star, u star and a star is equal to rho u and a. Here we mean star by the velocity, area and density corresponding to Mach 1 case. In our earlier case we had a CD nozzle, and then we will assume that now our nozzle is choked, or our nozzle has a condition which is Mach 1 in the throat. So density, velocity and area in the throat, which gives Mach 1 for the nozzle, gives its mass flow rate through this section, and this mass flow rate is equal to mass flow rate in any section. So we are considering this rho u a in any section, and this rho star u star a star is mass flow rate only through the sonic section. Then a by a star is equal to rho star by rho into a star by u. So this is sonic velocity, since we have Mach number 1 over here. So this u star is basically a star. So this rho star by rho can be replaced as rho star by rho naught into rho naught by rho into a star by u. Here rho star is the stagnation density at the inlet, and it is constant throughout the isentropic flow. Hence we have rho naught upon rho is equal to 1 plus gamma minus 1 by 2 m square bracket raised to 1 upon gamma minus 1. We have derived this relation in our last class. Further, if we keep Mach number is equal to 1, then we can as well obtain the relation which is rho naught upon rho star, which is equal to gamma plus 1 by 2 bracket raised to 1 upon gamma minus 1. Further, we will take one relation known from the gas dynamics, that u upon a star, which is velocity at any point divided by corresponding velocity at Mach 1 state, is called as m star, and that m star is related with m. M is Mach number divided by the m is Mach number, which is velocity divided by local speed of sound, but that local speed of sound is a. Here a star is the speed of sound when Mach number is 1. Then putting these in this relation, but for this equation if we make a square of it, then we will get this relation, and in this we will keep all the equations whatever we have obtained. Then we will get relation which is a standard relation, which is called as a by a star, which is area and Mach number relation. Here area Mach number relation says us that if we know area at a particular location, and if we know a star, which is a location at which Mach number is 1, then that area ratio, if it is known to us for a given fluid, then we know what is the Mach number in the area cross section, which is A. So if A star is known, A star is, if this is a nozzle which is a convergent divergent nozzle, and then in this nozzle this is called as A star, which is minimum area at which Mach number is 1. Then if this area is known to us, then we can find out Mach number in any area. Suppose that this is A. This A upon A star is known from left side. Since we know these areas, we know which gas is flowing, so we know gamma. So we can iteratively work out and find out what is Mach number m in this cross section. Similarly, we can as well find out Mach number in any other cross section. So this is called as area Mach number relation. Then we will use this to find out choked mass flow rate. So mass flow rate at any section could have been taken by us, but we will take a particular cross section since we are interested in choking phenomena. And as we have seen, choking is said to be happened when Mach number reaches 1 at the minimum cross section. Since Mach number has reached 1, mass flow rate formula, which is rho into velocity into cross sectional area, would get replaced by, or can be particularly written for the minimum cross section area, where A star is throat area, U star is corresponding velocity, and rho star is corresponding density. But we know rho star upon rho naught is 1 plus gamma minus 1 by 2 bracket raised to minus 1 upon gamma minus 1. Further, this rho star will be replaced using this formula, and we can get m dot is equal to 1 plus gamma minus 1 by 2 bracket raised to minus 1 upon gamma minus 1 into A star into capital A star. But A star is equal to gamma r T star, and then this will be replaced and our mass flow rate formula will be updated as shown in the screen. So, we will alter this T star by saying it as equal to T star upon T naught into T naught, and then we know relation of T star upon T naught is equal to 1 plus gamma minus 1 by 2 bracket raised to minus 1. This relation is obtained for a very particular case where Mach number is equal to 1. And further we will say P naught is the total pressure is equal to total density into R into T naught. Keeping all these relations in this mass flow rate formula, we will get a big relation for mass flow rate as shown in the screen. This can be simplified since this term and this term is same. We have T naught over here and R over here. We also have R and T naught over here. So, thus the mass flow rate formula in a concise form will be P naught into A star divided by under root T naught into gamma plus 1 by 2 bracket raised to minus gamma plus 1 divided by 2 into gamma minus 1 into under root gamma r. It is evident from this formula that mass flow rate depends upon gamma and total conditions for a given A star and also on a particular gas. So, if gas is changed, then choke mass flow rate will change. Since change in gas will change gamma and also it will change R, specific Cp gas constant, which is Cp minus Cv is equal to R. Further, it is also dependent upon P naught and T naught, and it also depends upon A star. Major takeaway from this formula is that once mass flow rate is choked, we whatsoever alter the pressure at the exit of the nozzle is not going to change the mass flow rate, since in this formula there is no term which corresponds to the exit condition. Okay. Now, this formula we could as well use for the steam, but it is difficult for us to find out what is the gamma and R for steam, and since it is a two-phase flow, situation becomes more complicated, but this mass flow rate formula, which is very particular for gas, is going to give us an idea about the nozzle flow and how nozzle will be choked and what will happen if nozzle is over expanded and nozzle is under expanded. This understanding we can carry forward for steam, although these conditions will be different at different pressure, means these over and under expanded conditions for steam will be at different pressures and temperature as that of air, but philosophically the flow pattern would be similar. So, in this case we will try to find out mass flow rate through nozzle for steam. We know from the first law and second law combined thermodynamics expression, TdS is equal to dH minus VdP, where so dH is equal to VdP, since we are considering the nozzle flow to be isentropic. So, TdS will be 0. So, dH is equal to VdP. So, but from the energy equation we also know that dH is equal to VdV, since we have derived an expression which says that H plus V square by 2 is equal to constant, and the differential form of that expression was dH plus VdV is equal to 0. So, knowing this, we can have other expression for change in enthalpy, which is minus VdV. So, this gives us dH is equal to minus VdV is equal to VdP, and now if we integrate all the three sides, we get integration dH is equal to integration minus V dV is equal to integration V dP. But this is integration dH is equal to H2 minus H1, which is enthalpy at the exit minus enthalpy at the inlet. And this V dV integration will be V1 square minus V2 square by 2, since it has minus sign before it. And this V1 is the velocity at the inlet and V2 is the velocity at the outlet. But if we say that at the inlet we have stagnation condition, so H1 is equal to H0, and since at the inlet condition is stagnation, we have V1 is equal to 0. V1 is equal to 0. So the same expression can be rewritten as H minus H0 is equal to V2 square by 2 VdP. Okay, this is H2 minus H0 is equal to minus V2 square by 2 into VdP integral from inlet 1 to outlet 2. Further, we will also write down this expression in positive line, that H0 minus H2 is equal to V2 square by 2 is equal to minus V dP. But we know PV raised to gamma is equal to constant, or P upon rho raised to gamma is equal to constant, and let that constant be K1, which is called as isentropic. Here this K is an isentropic index for steam. So we have P0 V0 raised to K is equal to PV raised to K is equal to constant. So we have V over here, and this V can be replaced by P0 V0 raised to K bracket raised to 1 by K divided by P raised to 1 by K. So this can be put over here, and then we have H0 minus H is equal to V2 square by 2 is equal to plus P0 V0 raised to K bracket raised to 1 by K. Okay, that's why we will have an expression which says that we will have H0 minus H is equal to V2 square by 2 is equal to we have this expression written as negative H2 minus H0 was said as H0 minus H2 minus V2 square by 2 said as V2. So we multiplied all the three sides by minus 1, so we have minus here, and so we also have minus over here. So now we are integrating this expression from state 0 to state 1, or practically state 1 to state 2. So we have H0 minus H2 is equal to V2 square by 2 is equal to K upon K minus 1 P0 V0 minus P2 V2. So we have H0 minus H is equal to V2 square by 2 is equal to K upon K minus 1 into P0 V0 bracket raised to 1 minus P2 upon P0 bracket raised to K minus 1 upon K. Since we have taken P0 V0 common from this bracket, so we have 1 minus this. So this gives us the velocity at the exit of the nozzle. So now we can know what is the velocity at the exit of the nozzle, since this formula will be used to find out velocity at the exit of the nozzle. So we should know what is the condition for the boiler for our steam power plant, since boiler corresponds to maximum pressure and maximum temperature, and it is the steam turbine inlet, and the steam turbine inlet means practically for us a nozzle inlet. So for the nozzle inlet we have stagnation condition. So if we know stagnation condition and if we know nozzle exit pressure, which is P2, then we can find out velocity at the exit of the nozzle. So the mass flow rate formula we will continue. M dot is equal to rho AV. So M dot is equal to rho 2 A2 into V2. So we have just now derived a formula for V2, and we can say it is equal to A2, and this A2 appears over here. We wrote V2 as what we wrote in the last slide, but we also have V2 and this V2 is taken inside the square root by V2 square, and this gives us, with readjustment we are multiplying numerator and denominator over here by V naught, so it is V naught square upon V naught, and then we are also saying 1 as V naught square divided by V2 square and V naught square divided by V2 square. So we are multiplying it, since P upon V naught upon V2 square is equal to P upon P naught bracket raised to 2 by K. So we can use this by this formula which says that 2 upon K minus 1 P naught divided by V naught bracket raised to this. This leads to the formula m dot is equal to P naught divided by V naught bracket into the bracket P upon P naught 2 by K minus P by P naught K plus 1 by K. If we differentiate this expression by P upon P naught, we can and equate it to 0, then we will get a state which is a choked mass flow rate condition, which corresponds to P star upon P naught, and it is equal to 2 upon K plus 1 bracket raised to K plus 1. So we can find out critical velocity in the nozzle, which corresponds to V star. That means when the steam has reached Mach number 1, and that corresponds to 44.72 into H naught minus H star. Basically we had seen that dH is equal to VdV. So kinetic energy change is equal to change in enthalpy. So change in velocity is equal to square root of change in enthalpy. But here, as the steam table gives enthalpies in kilojoule per kg, so enthalpy in kilojoule will be multiplied by 1000, make it in joule. So this 1000 into kinetic energy will have V square by 2, so that 2 will be multiplied. So square root of 2000 is 44.72. Assumption over here is inlet velocity to the nozzle is negligible. Under that fact, we can find out the critical velocity or the velocity which gives us Mach number 1 in the nozzle. That velocity can be found out using this formula. So otherwise also we can find out, we can use the formula for V2, which is equal to 2 by K upon K minus 1, where K is the isentropic index, into P naught V naught into bracket 1 minus P upon P naught bracket raised to K minus 1. But when the velocity is to be found out for the critical case, we mean that P is basically P star, and so P star upon P naught relation is known to us, which is 2 upon K plus 1 bracket raised to K minus 1. So putting this in this equation, putting this formula in this equation, we can find out V2 is equal to 2K upon K minus 1 into P naught V naught bracket 1 minus 2 upon K plus 1. So V2, which is a critical velocity, is 2 by K upon K minus 1 P naught V naught into K minus 1 upon K plus 1 into the square root. Further, this K minus 1 gets cancelled. So we have 2K upon K plus 1 P naught V naught square root is the critical velocity formula for the steam corresponding to the Mach 1 condition. Now from the experiments, people have found out that K, which is an isentropic index for superheated steam, is around 1.3. So this formula will become 1.06 P naught V naught, and for dry saturated steam the K value is 1.135. So for this the formula becomes 1.03 P naught V naught. Here P naught is in Newton per meter square and specific volume is in kg per meter cube. So these formulas can be used to find out critical velocity in the nozzle. Now we are going to see what is the term which is called as nozzle efficiency. Here actually we expect if there is a nozzle, then it will have certain inlet and certain outlet, and nozzle flow is said to be isentropic. So, on HS diagram, where H is y axis, S is x axis, we expect the line to be vertical. Let us say that state is 3 at the inlet and state is 4 dash as the outlet, and this vertical line is isentropic. So, this is the ideal expansion of the flow in the nozzle, but in reality we get a point 4 at the outlet where we deviate from the reality. So, nozzle efficiency is said to be the actual enthalpy drop divided by ideal enthalpy drop. So, actual enthalpy drop is H naught, which is the stagnation enthalpy at the entry to the nozzle, minus H, which is the enthalpy at the outlet of the nozzle, divided by H naught minus H dash, where H dash is ideal enthalpy at the exit of the nozzle. So, this formula in the current context as 3, 4 dash and 4 becomes H 3 minus H 4 divided by H naught minus H 4 dash, where H naught is equal to H 3. So, H 3 minus H 4 dash. We can as well write down this formula in terms of velocity, since we know change in enthalpy is equal to change in kinetic energy for the flow. So, V 4 minus V 3 square is change in kinetic energy of the flow in reality, divided by V 4 dash minus V 3 dash, which is change in kinetic energy in ideal sense. For small velocity at the inlet means V 3 is to be almost 0. We can write down this formula as nozzle efficiency is equal to V 4 square divided by V 4 dash square. So, let the velocity coefficient be phi, which is V 4 upon V 4 dash. Then in that case nozzle efficiency is said to be phi square. We have to know one new term which is called as velocity coefficient, and that term is said to be phi. Now, further we are adding one more terminology, which is nozzle discharge coefficient, which is equal to basically coefficient of discharge, which says that actual mass flow rate through the nozzle divided by ideal mass flow rate through the nozzle. Here, if we are having nozzle which is non-ideal, then for non-ideal nozzle, if I want to find out choked mass flow rate, critical velocity, then the velocity formula, which was just this earlier for ideal case, would have nozzle efficiency multiplied, since now these enthalpies were ideal enthalpies. So, the reality will have the velocity at the exit of the nozzle or critical velocity at the throat is equal to 44.72 into the square root H naught minus H star into nozzle efficiency, where these enthalpies are in kilojoule per kg. This is for choked nozzle condition, but if nozzle is unchoked, then we will not have H star, we will have any H as H dash, which is the isentropic exit enthalpy to the nozzle. Now, we are going to see what are the types of nozzle. There are basically two types of nozzle. One nozzle is called as round nozzle or rimmed nozzle, and other nozzle is called as foil nozzle. So, in case of round nozzle, we have basically them mostly used in impulse turbines. These nozzles are very conventional, they are low cost nozzles, easy to fabricate, so easy to manufacture. Foil nozzles are costly and they are used for large steam turbine applications. Further, problem with rimmed or round nozzle is they are having low efficiency, they are large length nozzles or long length nozzles, and to avoid flow separation, the divergence angle in the nozzle is limited to be around 12 to 15 degree. But in case of foil nozzle, they are high efficiency and then they are short nozzles. So, these two are these nozzles. So, we can see this is a convergent divergent type, or maybe only convergent or only divergent type nozzle is this, which is rimmed or round nozzle, and foil nozzles are basically the passages between two aerofoils. The passage between two aerofoil will act as nozzle. So, here we have to fabricate the aerofoils, and so aerofoil fabrication is not that simple as the round nozzle. So, this is the foil nozzle and this is round nozzle. There are some more details we can see over here. In case of steam turbine, flow will come axially. In case of axial turbine, and flow will go axially. So this passage between two aerofoils will act as nozzle, and this nozzle is basically a stator. Then once the steam passes through the stator, steam would go from the rotor. So there will be stator and rotor combination, and that stator and rotor combination would act as the complete stage of a steam turbine. So this is the passage between two aerofoils, where P is the distance between the edge, trailing edge of the aerofoil, alpha is the angle which is the flow deflection at the angle at the exit, and then T is the local thickness of the aerofoil, O is the distance perpendicular to the flow at the exit, and Hn is the height of the nozzle in the exit. So this terminology is given over here, and knowing this terminology we can find out different quantities which are required, which is area which is exposed to the for the flow, which is O into Hn into number of such nozzles around the perimeter of the turbine. So O is equal to P sin alpha minus T. O over here is P sin alpha minus thickness. So but N is number of such nozzles, which is pi dm by P. This gives us total number of nozzles present. So keeping all these terminologies in this formula, we can get area of the nozzle is equal to pi dm Hn sin alpha into bracket 1 minus T upon P sin alpha, and this term can be said to be equal to Km, which is called as nozzle thickness factor. Now we can use these relations and this understanding for further analysis of the nozzle flow in the steam turbine, and those details we will see in the next class. Thank you.